I chose to do problem 2. The problem statement says, Dr. Darnton is performing a simple experiment to measure the force on different types of dipoles. In this experiment, a small plastic ping pong ball of mass capital M and radius capital R is given an unknown negative charge uniformly spread over its surface. The ball is hanging from a thread and can move freely. A distance capital L directly below the center of the ball is a small permanent dipole with known dipole moment P equals QS and mass M oriented as shown in the diagram. Part A states, calculate the charge on the ping pong ball required for the dipole to levitate motionless in midair. So, because it's not moving, we know that the sum of the forces has to equal 0. The only two forces are the force of gravity and the force of the dipole. We know that the force of gravity is equal to mass times gravity. Next, the force of the dipole is equal to the electric field of the dipole times the charge of the ball. The electric field due to a dipole is equal to K, the constant, times 2 times Q times S divided by R cubed. This simplifies to 2 times Q times P, which was given as QS in the problem statement, divided by capital L cubed, which was also given in the problem statement. Combining this with the force equation for a dipole, you get 2 times Q times P times capital Q over L cubed. Setting this equal to 0 and adding in the force due to gravity, you find that the force due to gravity equals the negative force of the dipole. By simplifying, you get that Q equals negative mass times the gravity, mass of the dipole times gravity, times capital L cubed divided by 2 divided by K divided by P equals the charge on the ping pong ball. Part B states, using a pair of tweezers, Dr. Darnton carefully twists the dipole 90 degrees clockwise without displacing its center of mass. Briefly describe the effect that this would have on the ping pong ball. Originally, the electric field was going up based on how the dipole was oriented. Now, with the positive end of the dipole on the right and the negative end on the left, the electric field will be going to the left on the ping pong ball. This means that the ball will be forced to the right because the ball is negatively charged, and the ball will go against the negative electric field. Part C says, Dr. Darnton repeats this experiment, but replacing the permanent dipole with a neutral atom of mass M and polarizability alpha. Calculate the charge on the ping pong ball required for the neutral atom to levitate motionless in midair. This is very similar to Part A, only now P is no longer just Q times S. P is now equal to alpha times the applied electric field. So, to find the applied electric field, you use the charge due to the ping pong ball, which is equal to K times capital Q divided by L squared. Plugging that into the equation above, right at the beginning of Part C, you get that mg equals negative 2k alpha times k again times q squared divided by L to the fifth. Solving for q, you get that q equals plus and minus the square root of mg L to the fifth divided by 2k squared alpha.